In 2011, the U.S. consumption of fuels for electricity generation in quads was as follows. Coal 18.04, natural gas 8.05, petroleum 0.29, nuclear electric power 8.26, renewables 5.14. Calculate the total energy consumed during the year in gigawatt hours. If gross generation of electricity in 2011 was 14.82 quad, what was the average heat rate for the entire system? To solve this by applying the GFSA method, of course we're going to start by writing our givens. In this case, they're primarily related to these numbers here, and those have units of quads, and what that's telling us is that that's how much energy was consumed. Fuel energy was consumed. So the symbol for energy is E, and so we're going to use the symbol E, and then we're going to say, okay, E for coal, for example. So E coal, and that's 18.04 quad. QUAD. So we're going to do that for all of them. We had energy contained in the natural gas that was burnt. That was 8.05 quad. Next we had petroleum. Not terribly common in the electric system, so not much of it at 0.29 quad. Next we have nuclear power, so we'll just give that the subscript N, E sub N. Well, that was 8.26 quad. And then we have renewables. Energy contained in renewables is equal to 5.14 quad. So that was all the energies related to the inputs of the fuels. We were also given the output of the generation fleet gross, which was 14.82 quad. We'll just call that E out, and that's 14.82 quad. So we've given them all symbols. We've given them subscripts that relate to something unique about them so we can identify them individually. So that takes care of writing our givens. Next we have to say, well, what is it that we are being asked to find? And we were asked to calculate the total energy consumed during the year in gigawatt hours. So this is the energy that was in the fuels individually. It's in quad. So what that's asking us is to add those up and convert it over to gigawatt. So that's E total input in gigawatt hours. That's one thing we were asked. And then we were asked what the average heat rate for the system was. So average heat rate. Okay, so the solution is going to start by just summing up all of these numbers. So E in is just the sum of all the fuels. So that's just going to be 18.04 plus 8.05 plus 0.29 plus 8.26 plus 5.14 plus 14.82. So we're just summing all of those up, and we get an answer of 39.78. And I didn't do any conversions there. All those were in quad, so that's 39.78 quad. So now what I need to do is go ahead and convert that over to gigawatt hours, which is what the question asks for. So I need to use a couple conversion factors there. So I'm going to use 39.78 quad as my base, and then I need to cancel some units here. So from the table given in the chapter of energy units, I don't have a quad to gigawatt hour conversion, so I'm going to have to use an intermediate energy unit. In this case, I'm going to use joules, the most common one for intermediates. And so that's 1.055 times 10 to the 18th joules in 1 quad. So if I multiply those out, I'm going to convert that over to joules. Still not what I wanted, so I need to go one more conversion at least. Next, I want to go from joules to kilowatt hours. So I've got 1 kWh is equivalent to 3.6 e to the 6 joules. 3.6 e to the 6 joules. And I still wasn't, not quite there. I'm close. I'm at kilowatt, but I want gigawatt hours. And there are 10 to the minus 6 gigawatt hours in 1 kilowatt hour, or there are 10 to the 6 kilowatt hours in 1 gigawatt hour, however you want to write that. So anyway, you perform this dimensional analysis or unit cancellation. So we'll see quads cancels with quads, joules cancels with joules, kWh cancels with kWh. We're just left with gigawatt hours here. So we've got all the conversion factors that we need, and that gives us 1.1658 times 10 to the 7th gigawatt hours. And so that's E in total. So we've solved that one right there. Next, we were asked to determine what the heat rate was, and we know the formula given in the chapter was that the efficiency of the system is equal to 3,412 BTU per kWh. That's just the numbers of BTU in a kWh. It's just basically writing 1 over 1 divided by the heat rate. So we don't have efficiency, we don't have heat rate. This is a constant, so of course we have that. So what that tells us is that we need to figure out what efficiency is, and efficiency, once we solve for it, we can plug it in and solve heat rate by just saying heat rate is equal to 3,412 divided by the efficiency of the system. So once we get that efficiency number, we can just plug it right in there. The efficiency of a system is defined as the ratio of the output energy or power or whatever to the input energy, power or whatever. So in this case, we're looking at total energy conversion efficiency, so we want to know the output energy to the input energy. So we were told that in 2011, that was 14.82 quad was the amount of electricity used. So we got 14.82 quad. And then the input energy we had calculated up here is 39.78 quad. We want to keep it in quad so that the units cancel. See, quad with divided by quad, those are going to cancel. And we get that, that's 37.3% efficiency. And so that tells us that the heat rate is 3412. We want to put the heat rate, the efficiency in a decimal number, which was 0.373, and that's going to give us a heat rate 9147.45, and then heat rates are in BTU per kWh. So we've got a average heat rate for the entire electrical system of 9,147.5 BTU per kilowatt hour. And that's the second thing we were asked to find. And so we're done with the problem.